Good morning to everyone present, whoever is watching this presentation. My name is Nihar Boro, and with my partner Dhiraj Rahang, today we present the project BTech final year presentation of the title Design of a High Frequency Dimensionally Tunable TZ based comparator for 5G applications. We present this project under the guidance of Mr. Manas Pratim Sharma, our guide, and also under the supervision of Professor Pandharva Kumar Sharma and the co-guide Dr. Surajit Deka. So let's start the presentation. So outline. So the first slide provides the outline of what about the structure of the presentation. So we have introduction, motivation, literature review, problem identification, design objectives, block diagram results, conclusion, limitation, future direction, and then finally the references. So introduction. So the data converters, which we know, the analog to digital and the digital to analog types converter, are the fundamental types of devices that convert one type of signal to another form of signal. So if there is an analog signal which we want to convert to a digital signal, we use an analog to digital converter, and if it is the reverse, we want to convert a digital to an analog, then a DA converter is used. So these types of converter are always have been designed, and from history till now, that these types of converter have specific purposes. So all different types of converter are designed according to specific specifications, and there is not a general rule of thumb to conclude how these converters will perform. But in general, for most types of converters, they are designed to be fast. As for the analog to digital conversion, the faster conversion and the converters, they perform a bit better than the slower types of converters. This is because in current generation, the need for speed has arisen as we are moving towards more high speed performance devices and applications. So let's start the presentation. And there is the ADC. So inside the ADC there are many types of components. So in the components there is a comparator. So the comparator, what is a comparator? The comparator is a decision making circuit. So it compares one voltage level to another voltage level and outputs based on the comparison. So let's proceed to the next slide. Motivation. So in motivation, why we have took up this project is that there are many types of analog to digital converters which use different types of comparators. So these comparators are all designed to perform according to the needs of the ADC. And generally these types of converters are high speed, but they are not as fast as reaching levels of 10 gigahertz, 12 gigahertz of frequencies. So we have decided to take up a project which performs decently at high gigahertz frequency levels, and therefore, and also the converters, specifically the comparators, should be able to perform at 5G frequencies, the mobile 5G frequencies. So this was the motivation for our project. These are the literature review. We have used many more reviews, but for the presentation these are the main 5 ones which we have presented here. Problem identification. So the main problem identification is that all types of converters have some limit, and therefore all types of comparators are also limited. Some comparators only perform at megahertz frequencies, and these types of comparators are used in the ADCs, and the ADCs are pipelined to perform in much higher frequencies like the gigahertz range. So the design of comparators can be said to be limited according to the ADC architecture. So if we design a comparator that is fast, that can perform in multiple frequencies according to the user, and also the comparator is adjustable according to the dimensions of the design, which is the dimensions of the MOSFETs, So it will be a very beneficial part from our side. So that is the main problem identification. Design objectives. So the main goal of the project is to achieve distinct higher and lower voltage levels for proper logic realization, to have logic realization at higher frequency bands, also to have multi-frequency operation with dimensional tuning. So these are the main objectives for design. So let's talk about the conventional comparator. The comparator is, as we have discussed, is a decision making circuit which compares to voltage levels. According to the voltage inputs, the output is decided. If the voltage is Vp is higher than the voltage at Vm, then the output is a high logic level, and if it is reverse, then the output is a low logic level. So the conventional comparator, which is in the books, is a high performance voltage comparison unit. It mainly consists of 3 stages. So this is the block diagram highlighting where the comparator exists. So the conventional comparator has 3 stages. These are the pre-amplification, the decision circuit, the post-amplification. So in the pre-amplification stage, uh, it, it is such that the input signal is amplified to a certain threshold, because until the decision circuit works and then the final output we get, sometimes the output levels are not as quite good. So therefore pre-amplification is done before the decision circuit is used, and in the decision circuit it is obvious that the signals are compared, and in the post amplification the signals are amplified again through a buffer. So let's start the phase 1 circuit. So the phase 1 objective, let's come to the design objectives of phase 1. So in phase 1 the comparator should be able to perform in gigahertz range covering up until 6.5 gigahertz, and that is the 5G frequency range for the mobile communication bands. And the dimensional aspect of the design should be such that if we try to use a certain frequency, we can adjust the dimension to better optimize the output. So that is the meaning of this line, dimensionally tunable for different frequencies. So the transistor size should be dimensionally tunable for optimal results. And also it should be multiple frequency operation. It should be able to operate in 5 gigahertz, 3, 1, 6, according to the needs of the user. So this is the MOSFET comparator in 19 nanometer technology. So the design of the comparator is completely MOSFET based. That is, we have PMOS and NMOS in the circuit, and it is made in 19 nanometer process technology using an EDA tool. The logic of the comparator is dynamic logic, the dynamic CMOS logic which we have read in the books. So the comparator mainly consists of a gain stage and a latch stage. The gain stage takes the input, it amplifies to a VDD, and the latch stage stores the value, and the output is taken from the latch stage. So after that there is a transistor which discharges the output nodes towards ground. So that is the main working principle of the comparator, and the decision of the comparator is done when the clock is high, as it uses the pre-evaluation logic. So at clock 0 it's the reset phase, and at clock 1 is the decision phase according to the decision of the circuit that is designed. So this is the circuit design of the circuit diagram of the comparator, and this is the schematic of the comparator in the EDA tool. So let's come to the experimental results of the comparator. These are the transient responses of the comparator at various frequencies. Seen, the comparator performs at 1 gigahertz to at 3 gigahertz, and also at 6 and 7 gigahertz, and also at 7 gigahertz with a capacitive port. So we have seen that the transient response is done till 7 gigahertz. Parametric analysis. So in parametric analysis we have shown how the delay of the comparator varies with the size. So in the first graph we can see that as size is increased, so the delay decreases to certain level and then it starts to increase again. And below we are seeing the power dissipation versus the size. So the power dissipation increases, as we all know that if the size of the transistors are increased, the power distribution will increase. Results comparisons chart. Okay, so in this chart we have shown the overall results of the comparator. So the transistor size, which is default at 7 gigahertz, it gives a V output high of 1.21 volt and a V output low of 36.6 millivolts, with a decent power and delay of 42 microwatts and 56 picosecond respectively. After the transistor sizes are adjusted, the V output low has reached as low as 900 microvolts. But we can see that even at 9 gigahertz, that is above 7 gigahertz, the transistor size that was adjusted has a V output low of 100 millivolts. So we can see that it does not perform quite well at frequencies beyond 7 gigahertz, because since the comparator has a distinct window for high logic realization and low logic realization, 100 millivolt is quite much for the low logic realization level. This is the general delay analysis table. So here all the frequencies from 1 to 7 gigahertz are shown without load and with load. So we can see from the table that the delay at 7 gigahertz is quite low, which is 55, which is only 56 picoseconds, and even at capacitive low, it's 63 picoseconds. So that is quite fast. You can say the comparator is very fast and working. So this is the temperature analysis. So the temperature was varied from 15 to 15 degrees Celsius to 50 degrees Celsius, and we can see that the power dissipation and delay are all approximately same. So we can say the comparator is versatile in different temperatures. So this is the comparison with the references. So the work which we have presented in phase 1 has achieved 7 gigahertz of Fmax. So the references, one of the references 100 megahertz and the other at 3 gigahertz. So the size, also the size adjustment, you can see we have adjusted the transistor size, and the power dissipation according to a high frequency operation is also quite good, only 44 microwatts with a delay of 55 picoseconds, which is the least among all the references. So we can say that we have provided a little better output than the references. So the limitations of the comparator designs, is that it cannot perform beyond 7 gigahertz. And beyond 7 gigahertz, the logic level is around the low logic level, digital level is around 100 millivolt, which is not good for optimal realization. Phase 2. So the phase 2 design objectives. Also, we have completed the design objectives of phase 1, which were dimensionally tunable, which was done as we have applied transistor sizing adjustments, along with covering all the frequencies till 6.5 gigahertz. So the circuit performed at 7 gigahertz of max frequency. So we have fulfilled the objectives of phase 1. So in phase 2 objective, we have it should even perform higher frequency than the limit that was achieved in phase 1, and also there should be new design implementation in the structure, and it should be dimensional tunable with multiple frequency operation. So the comparator design, which was done in phase 1, was modified by using of transmission gates at the inputs of the main circuit. So this is the first design of the 2 designs that were done in phase 2. So the transmission gate is applied because we have seen that the logic low level had some problems. So therefore we have implemented the transmission gates for good strong high and strong low levels for the circuit, and also the size of the transistors were again changed according to different frequency levels. So this is the circuit diagram of design 1. So if we compare the 2 circuit diagrams, at the input we can see there are 2 transmission gates for the positive and the negative inputs. This is a symmetric diagram. These are the experimental results at 7 and 9 gigahertz. So we can see that now we can perform at 9 gigahertz. Before it was only 7 gigahertz. So this is the comparison chart of this design. So we can see that at default size the V output low is 30 millivolt. At 7 gigahertz with adjusted transistor size it's only 350 microvolts, and at 9 gigahertz that's only 1 millivolt. So we have come a long way with the implementation of TG and the transistor size adjustments, along with good power dissipation and delay. This is the same as phase 1. We have done parametric analysis to show how size affects the circuit. This is the parametric analysis of the voltage versus reference. We have also seen that when the reference voltage is increased from to not from to higher levels, the V output low is actually really bad. It increases along with the increase with the reference voltage. So what we have demonstrated in the below graph is that the V output low is again affected by the size of the transistors. So even in higher reference voltages, we can see that if we adjust the transistor size accordingly, we can even reduce with that particular reference voltage. So it is again dimensionally tunable for different reference voltages also. So we have achieved another dimensional tunable aspect in phase 2. This is the general delay analysis table. We can everyone can go through it, and we can find that the delay is still good at 9 gigahertz. It's only 51 picoseconds. The temperature analysis also shows that it's good in all types of temperature. So let's come to the design 2. In design 2, the transmission gate is applied to the tail transistor of the main circuit instead of the input, because we have also seen that the tail transistor affects most of the discharge through the ground or through the pull down network. So that is why a single TG is applied at the tail transistor, and also it reduces the number of transistors by implementing a single transmission gate instead of 2 transmission gates. So this is the circuit diagram of the design 2. Schematic experimental design. Same types of experiments are done. We can see that in the design 2 of phase 2 is also well performing at 9 gigahertz. Yes, this is the results comparison chart. Similarly, we have shown the adjusted transistor sizes and output high and low voltage levels. The parametric analysis is shown similarly for this, with the voltage versus reference and voltage versus size also. Delay analysis, yeah, this is also done at 9 gigahertz. You can see it's good with 55 picoseconds, though it is a bit higher than the design 1, but still it has less transistors. Temperature analysis again shows how it is good even at higher temperatures. So this is the this is the comparison among the 3 different designs of the phase 1 design and the 2 designs of phase 2. So if we look at this chart, we can conclude that the maximum operating frequency is achieved to be 9 gigahertz in the final design, in the final 2 designs of the phase 2, but the last design uses 1 transistor less than the first design of phase 2, and also the output low level of the last design is only 800 microvolt, whereas the design 1 has 1 millivolt, and the main design in phase 1 had 100 millivolts. So therefore we can conclude that the last design is better compared to the other 2 designs. This is the comparison of work with the references. Okay, so let's continue. This is the comparison of work with the references. Reference 1 and 2 is taken again, and we can see from this table that the last design, phase 2 design 2, achieves the most better result comparing to all the works. So in result discussion, we have seen that in phase 1 the circuit operated at 7 GHz of max frequency. In phase 2 we have exceeded that and reached 9 GHz. Sorry, 7 GHz in phase 1, and in phase 2 9 GHz. So in phase 2 again we have implemented new designs, and we have adjusted the transistor size for the reference voltages and different frequency levels. So both the design objectives of phase 1 and phase 2 of the project has been fulfilled, and we have also achieved better results than the references. So in conclusion, let's come to the conclusion. We can see that the results are good even at 9 GHz. The final design can perform at 9 GHz with good power dissipation and delay, and also with good logic levels. So the limitations of the final design is that it can only perform till 9 GHz now. Yes, it can perform beyond 9 GHz, but for that more complex optimization levels are needed to be done. Complex optimization algorithms like some machine learning algorithms or even different circuit structure, so that can be done. So that is the limitation. Also the power consumption and delay can be improved. So the future direction, as we have said, for the limitation it cannot perform beyond 9 GHz. So in future directions, if further optimization is done, then more operating frequencies can be achieved, and also the power and delay can be reduced as well through some other complex optimization algorithms with a good output, high and low logic levels. These include all the references we used. So thank you. So this was the project presentation of Group F from Nihar, Jyoti, Boro and Dhiraj Rahang under the guidance of Mr. Manaspati Sharma and Professor Pandra Kumar Sharma and co-guide Dr. Surajit Dekha. So thank you everyone.